everyone. I think we'll look at a couple of problems here for AC circuits. I think these are the problems people ask questions about in class on Wednesday. If I got them wrong, let me know. And we'll look at a couple of different problems. So we're looking at problems 67 and 68. I think it was in fact part D of 67 and part A of 68. We'll look at part A of 68 and all of 67 since we need that stuff from A, B, and C to do part D, and it's relatively easy for us to work through it. So we're going to do 67 and 68A out of the book here. It says a motor attached for 67. It says a motor attached to a 120 volt 60 hertz power line draws 8.0 amps of current. Its average energy dissipation is 800 watts. What's the power factor? So part A here is asking the question, what's the power factor? And we're just going to say cosine of phi is that power factor is equal to P over I RMS. The voltage driver RMS is equal to 800 watts over, what was the, 8 amps times 120 volts is going to be 0.83. So that's cosine of the angle there. Part B asks us what is the RMS resistor voltage. So part B, we want to look at this and say for the resistor, the potential drop across the resistor is related to the driver EMF via this power factor. So this is E RMS cosine of phi is going to be equal to 120 volts times 0.833. That was the extra digit that was up there, was a 3, and that's going to be 100 volts. Part C asks us what is the motor's resistance. So what is R in there right now? And R is going to be related, we just use Ohm's law here. R is VRMS that we just found over IRMS, which we had earlier. So that's 100 volts divided by 8 amps is, what did I get when I did that? 13 ohms. Part D, which is where I think the question arose, was how much series capacitance needs to be added. So what extra capacitance would you put in this circuit in series with the other capacitance that's already there? Needs to be added to increase the power factor to 1. So in this case, we want the power factor to go to 1. That means cosine of phi is equal to 1, which means phi needs to go to 0. If we want to add capacitance to make this happen. And so what we can look at there is to say right now what we have is this. Let's go and figure out what our capacitive, how our capacitive, basically what we're saying, okay, is remember that the tangent of phi, or phi, let's look at that, we do the tan inverse. So the phi is the tan inverse of the inductive reactance minus the capacitive reactance divided by the resistance in the circuit. And so we want that to be 0 now. So that means we need x sub L minus x sub C to be equal to 0 is the way we're going to get that angle to go to 0 like that. And so we can ask, what is x sub L minus x sub C before we have this extra capacitance? How much capacitance do we have to add to make that go to 0? So right now, x sub L minus x sub C before we add anything is going to be R times tangent of 33.6 degrees, so that's phi. Let's back up a step and make sure we know what we're doing right there. Phi, the current phi that we have, this is what we're trying to get to. The phi that we have up here is going to be the cosine inverse of that. So phi now is cosine inverse of 0.83, and that's going to give us 33 degrees, if I remember correctly. Yeah, 33.6 degrees is the current angle, and that's got to be. We can then come up here and say, now currently x sub L minus x sub C. Now, before we add any capacitance to the circuit, x sub L minus x sub C is 12.5 ohms, and times, we're doing this, so to say tangent of phi is equal to x sub L minus x sub C over R. So we're bringing this R up to the other side. That's that R times tangent of 33.6 degrees. Let's see what I got there when I did that. That's 8.292 ohms is what I got. And so that looks pretty good. We need this to go to 0. So we need that x sub L minus x sub C is 8.3 ohms. We need to add 8.3 ohms of capacitive reactance. So we need the additional C that we add to this circuit has got to be, we need the C that's added to be, remember that x sub C is 1 over omega C. So we need C to be equal to 1 over omega x sub C. That's now that 8.292 ohms. It goes in there. So this has got to be 1 over 2 pi times 60 hertz is our omega times 8.292 ohms. And when I stuck that in, I got 3.2 times 10 to the minus 4 farads. 3.2 times 10 to the minus 4 farads. That's the extra capacitance that has to be added to this circuit to turn this phi to 0, which is basically what they were asking for, to say the power factor has to go to 1. So that's the problem 67. Probably we should stop this and restart it for the other problem, but I'm not going to do that. I'm just going to plow ahead and see what we can do with 68A. So 68A here now asks the question. It says, the figure below shows the current and voltage graphs for an RLC circuit, and we want to know what the resistance are in the circuit. And we see that the peak voltage happens at time t equals 0 of 10 volts, and the current is half of the peak at time t equals 0, and the peak is 2 amps, and so it's 1 amp at time t equals 0. So from the diagrams, when we look at this, what we know from the diagrams is E naught is equal to 10 volts, and I max is equal to 2 amps. F is equal to 1 over 100 microseconds. I think we can see is 10 kilohertz from the diagram that we have. That's what I saw when I looked at the diagram. Now, at time t equals 0, we have I is equal to 1/2 I max, the maximum current, and so I over I max is equal to cosine of phi is equal to 1/2, and that tells us that phi, the phase angle of our circuit, has got to be 60 degrees. Okay, so that's what we got there so far. That's what I can tell from looking at the figures that they give to us. And so we know that tangent of phi is x sub L minus x sub C, as we just did a moment ago for the other problem, divided by R. X sub L minus x sub C has to be equal to R tan 60 degrees. Okay, and we also know that I in the current has to be equal to the EMF of the driver divided by Z. And so I max has to be E naught divided by Z. And so we get that Z equals 5 ohms, 5.0 ohms from that right there. So that's our impedance, is 5 ohms. That has to be equal to the square root of R squared plus X sub L minus X sub C squared. And we have what X sub L minus X sub C is right there. So we can stick that right in and to say this has to be equal to the square root of R squared plus R squared tan squared 60 degrees. Factor out the R squared, comes right out of the square root sign, and so we get 5.0 ohms has to be equal to R times the square root of 1 plus tan squared 60 degrees. Okay? So far, so good. So then we can say that R, just solve this for R, and that's 5.0 ohms divided by the square root of 1 plus tan squared 60 degrees. Sure I got that right, tan squared 60 degrees. And that turns out to be 2 when I stick it into the calculator, and I get R is equal to 2.5 ohms. So that's what I got when I worked through it. Anyway, so there's a couple of problems that we talked about in class on Wednesday for you to take a look at and figure out if you have some questions about it. So let me know if you have any further questions after looking at this, and take care. We'll see everybody soon.